Okay, so there are some properties that the wave function must have in order to be valid to be used for Schrodinger's equation in order to describe the electron distribution. Okay, and so the first one is that the wave function must be single valued. 2, it must be continuous. 3, it must approach 0 as the radius approaches infinity. 4, it must be normalized. And 5, it must be orthogonal to other wave functions. So let's illustrate what each of these means. Okay, so let's say we have a wave function. All right, where this is the value of the wave function, and we're going to make the x-axis some radius r. Okay, since we're thinking of, for instance, the position of an electron from the distance of the nucleus, right? Where the r, or the value of r, the radius, is telling you how far away the electron is from the nucleus in any given direction from the nucleus. Okay. Now, a acceptable wave function will be single valued. So, for instance, like if we draw a sine function, it looks something like this, right? Okay, we expect this would be a single valued function. Okay, and so a single valued function at any value of r, in this case, there's only one value associated with that. So I can pick r over here, all right, and I draw a line corresponding to where the y point is, or on the corresponding point on the y-axis. In this case, the value of c, right, that the wave function is defining, right, and there's only one value. So what would something that was not single valued look like? Well, let's say we transpose this function. Okay, and we had transpose this function, okay? Then, let's say we draw a line to the axis, the r-axis in this case, right? And what we see is that this line touches 2 points on the function, okay? This is not a single valued function, okay? And therefore, this would not be valid as a wave function for Schrodinger's equation, all right? So, we must be single valued, all right? It must be continuous. All right, so there's got to be continuity. So again, like a sine function would be a continuous function. What would not be is, say, there's a discontinuity. So let's give an example of what would not be valid here in this case. So let's say we have a function looks like this, where we have a non-inclusive point here, and then this picks up somewhere else on the y-axis. Okay, there's a discontinuity within this figure. All right, and so that would also not be a valid wave function. All right, so the wave function must be continuous. Finally, okay, the wave function must, as it approaches as the radius approaches infinity, the wave function must approach 0. And so, for instance, this would be acceptable because as this goes towards r equals infinity, as we continue to go right to increasing values of r, this is approaching 0. Would not be acceptable, for instance. This is something that has an asymptote, for instance, at 1. As it approaches infinity. This would not be a valid wave function. All right. So number 4, the wave function must be normalized. Okay. So in this case, what this means is that the integral of any wave function and its conjugate over all space, okay, where dt tells us this is over all space rather, okay. Whoops, forgot the a there. Okay, this has to be equal to 1. All right. So remember what we said before about what happens if we square the wave function. Okay, we get c squared. In other words, okay, we say what that does is that tells us the probability that at any given position the electron resides. Okay, so if we think of it this way, right, what normalization tells us is that there's a probability of 1 of finding the electron in all of space. Okay, and that should be that is a requirement for the wave function in this case. Is you must be able to find the electron somewhere in all of space. Okay, and then the wave function, the actual mathematical description of the wave function, tells you at what points within space it is more probable or less probable to find that electron. All right, but first we have to be able to say that we are going to find that electron somewhere in all of space. Okay, and that's what the normalization allows us to say, or ensures that we are saying. Okay, and finally, two wave functions must be orthogonal to each other. All right, so what that means, if you have two different wave functions, you just by the conjugate, we have an over space. What that means is that that has to be equal to 0. Okay, and so these are the criteria for a valid wave function.